Okay, welcome to the talk. I can see that there are quite a few people attending online. I'm going to talk about some of the research that we've been doing on memory-centric computing. As I mentioned, this is a very long talk, but we can keep it to 1 hour or so. And you can ask questions in the meantime or afterwards. So it's perfectly fine to interrupt me. Today, computing is bottlenecked by data. If you look at important workloads, machine learning, genomics, databases, etc., all are data intensive. They require rapid and efficient processing of large amounts of. On top of data is increasing, it's actually exploding. We can generate much more data than we can process today, and we want to do more sophisticated analyses on the data. Probably a lot of people know about machine learning and the growth and exponential growth of neural networks. This is a presentation by the CTO of Cerebras. These are folks who are designing wafer scale chips that are this big to co-locate computation and memory together. And the reason is that memory requirements are growing exponentially over time, and compute requirements are also growing exponentially over time. As a result, we're pushing the boundaries of computation significantly with emerging models that are coming up soon. And this is going to continue for a while, and clearly this is an important data and interesting and important data intensive applications that we use in our lives today. Some examples are over here. And if you look at those applications, data is a performance energy bottleneck. We go to memory and storage a lot. And on the other hand, there are many other data intensive applications on the edge or mobile devices as well. And data becomes a performance and energy bottleneck in those devices too. I'm going to very briefly take a detour on genomics. This is an area that we've been working on a lot. And this is an area where data is really exploding because we have sequencing technologies that can sequence DNA or RNA very fast today and very cost efficiently. If you look at this picture over here, this shows the cost per DNA sequence, and it's been reducing exponentially at a much faster rate than the transistor costs are reducing as dictated by Moore's law today. And the reason is new technologies have been introduced in sequencing devices that have made the sequencing much more cost effective. As a result, now we can actually generate a lot more data than we can easily process. And these are some examples over here. Now, we have these very good machines, but the problem is we have to move the data somewhere else to actually process the data, and then we need to do a lot of computation. So scientific discoveries and medical advancements are usually bottlenecked by how fast we can move and process the data. And clearly, there are many applications or use cases that can be built on genome analysis. I don't have time to talk about a lot of these, but you can read some of our papers and some of the other papers. But I will show you that this device over here, which is not very new right now, is a data generator. So this device is a genome analysis sequencer. It's very low cost. You can buy it for relatively cheap. It has actually enabled a lot of understanding the COVID RNA, for example, but many other RNAs and DNAs as well. Unfortunately, this is a poor device for data analysis. So you have to move the data from this device somewhere, usually a data center, and cause a lot of churn and energy overhead, and then do the processing somewhere else. And this is one of the reasons we have this mismatch. We have these great data generators. Unfortunately, our data analyzers are not keeping up. So this is one slide that I think summarizes the problem that we're facing in many domains today. On the left side, you see a genome sequencer. In the genome analysis domain, this is a very special purpose machine that can generate data, genomic data. And then on the right side, in order to analyze this data, you have to move that large amounts of data to some computer that's usually far away. And that computer is usually general purpose. So we have this fundamental mismatch between a special purpose machine and then data movement and then a general purpose slow machine. So I think we have this picture in many domains today. So this is genomics, but if you replace this machine with a video or many video cameras, video is very specialized also in terms of data generation, but data analysis is not specialized. And then you can also replace it with web clicks, internet, social media, etc. All of those are special purpose machines that can generate data. Okay, so I think we're going to tackle this problem in this talk. The general problem that we're going to tackle will be how do we actually process data in a much faster way without moving the data as much and while doing operations on the data as it's being generated or as it's being stored in our systems. But let me finish the genomics part. So genomics is very interesting, and we've been writing a lot of papers about it. This is one of the recent papers. Sorry, this is one of the recent papers that we published at Design Automation Conference, an invited paper. You can take a look at it. It's a short overview paper. And then we have also some primer papers that help people get into the field. And I recommend people to look into it because it's a very high performance application that's going to be a lot more important in our lives going into the future. And these are some papers you can find. I'll give you one example of what application. Today, high bandwidth memories like HBM, for example. So what this FPGA enables is processing of the data where it's stored in this HBM memory without moving the data further into a general purpose processor. And it also enables specialization of the logic that is used to operate on the data. So it tries to overcome these two bottlenecks that I mentioned earlier, data movement as well as specialization. And we've actually used the system together with IBM and changed the applications, in this particular case, two applications, genome analysis and weather modeling, and looked at the benefits of specializing as well as doing near memory computation. And you gain significant performance improvements. You can see some results over here, but I don't want to dwell on it. Clearly, you need to do a lot of work to decide what should be offloaded to the FPGA and how you should actually maximize the bandwidth that's there for high bandwidth memory. But if you do all of that hard work, you get significant performance and energy efficiency benefits, as you can see over here. Now, this is what you can do today. Today is good. This exists. Going forward, I think this needs to become more programmable. But I want to talk about the future. What should we do going into the future, and what kind of benefits we can potentially get, what kind of things we can enable. So we're going to talk about things that do not exist yet. Okay, so some examples of what doesn't exist is we've been looking at approximate string matching accelerators like this. You can take a look at this paper. We've been looking at other software and hardware co-designs. We've been looking at in-storage analysis of genomics, and I will, hopefully, if I have time, I will talk about this in a bit more detail. I have slides. And then we've been looking at accelerating sequence to graph alignment, which is an interesting problem. There are a lot of algorithmic issues as well as hardware design issues in this domain. We've been looking at other issues like integrating different steps of the genomic pipeline so that we don't need to move data from one machine to another machine to do the analysis. And more recently, we've been looking at accelerating base callers. This is a step where you take a signal that's generated by a nanopore device and convert it to text. And we try to actually do that much more efficiently by accelerating neural networks using FPGAs and also near memory engines. I don't have time to talk about this. A lot of our papers summarize this. If you're interested, I'd be happy to talk about it separately, but not today. And you can find a lot of talks on this topic. And we actually have a genomics course. If people are interested, all of our courses are online. People can attend it, they can learn, and they can also contribute. If they have questions, they can ask. We also organize workshops on this topic in different conferences. Recom is one of the major computational biology conferences. Okay, so this was actually all motivation. I've talked about this genomics application because it's an example application that really overwhelms our modern machines. That's true for many, many other applications. In the end, this huge amounts of data movement, and the need for analysis of the data overwhelms our machine storage and memory capability, communication capability, and computation capability. It also greatly impacts robustness, energy, performance, and cost. I'm going to mention that a little bit. Now, if we go back to the fundamentals, in order to build a computing system, you need to have three key components: computation, communication, storage, and memory. And these need to be put together somehow. If you look at the way we have been putting these together over the last 80 or 100 years, we've decoupled them. We've decoupled them separately, mostly, and we've introduced interfaces, rigid interfaces between them. And very importantly, we have specialized the computing unit such that it is the only place where we can do computation. So to be able to do computation, we need to move the data from the memory through the communication unit into the computation unit. We cannot do computation on the memory side or the communication side. And I believe that we need to re-examine this choice going into the future, because data is mostly in the memory and storage unit, and it moves through the communication unit. Very small amount of data actually can be kept inside the computing unit. We should probably be thinking of integrating these components in a different and better way and enabling computation across the entire system as opposed to just the computing unit. Okay, let me just give you some examples. I'll spend some time on motivation, and then we're going to talk about some new ideas. So this is my cartoonish picture of an existing system. It's a general purpose system, but it could be special purpose also. You can see cores over here. These could be accelerators too. And this is where the computation gets done. Everything else on the system, caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage, and other interconnects, they're all dedicated to storing and moving data. And if you actually do the calculation, more than 90% of the resources, real estate of a single node, a compute node, is dedicated to storing and moving data. Now, you would say that perhaps if we actually design our system this way, it's not bottlenecked by data, but unfortunately, our system is still bottlenecked by memory and storage. We're dedicating most of our resources to memory and storage, but we're still bottlenecked by it. This seems like a bad design decision today. We don't have a balanced system. Now, if you don't like my picture, this is a picture from AMD. This is AMD's chip in 2020. And you can see that this green box is L2 and L3 caches, most of the chip. And the rest of the chip is actually interconnect, as you can see. A lot of the computation units are very small because Moore's law has been very successful. Technology scaling has been very successful. We were able to scale logic very well. Unfortunately, memory structures and interconnects did not scale very well. And we also need a lot of it. So most of our chips are dedicated to this. And on top of this, we're adding more and more memory and storage. So this is AMD's 3D cache. This is actually beautiful technology. They were able to add a 3-dimensional bonding, stacking-based cache using through silicon vias on top of this processor. Unfortunately, this is not helping, basically, in many applications. It just adds more overhead, but it doesn't really significantly help performance commensurately to the amount of area that we put on our systems. Okay, if you don't like AMD, this is IBM. Very similar story. I don't want to spend a lot of time over here, but you can see that the green parts are L2 and L3 caches, and then a lot of the chip is still memory signaling, interconnect, etc. Right? Cores are a very small fraction. Okay, this is another system. It's a system on a chip, and you can see that this processor chip is a lot of SRAM in the end, and then there's DRAM, and then there's the darkness, which is storage. So most of these components are actually dedicated to storage and memory, and they cannot do computation. Only the very small fraction of this SRAM type of chip can do computation. I'm calling it an SRAM chip because mostly it's dominated by SRAM, right? Okay, now let's put some data on this bottleneck. So we've studied these workloads on the mobile or edge devices together with Google. And we spent a lot of time studying these workloads, actually analyzing. And we found out that more than 60% of the total system energy in executing these workloads is spent on moving data across the memory hierarchy. This is actually an optimistic number because if you actually use very large data sets, this number grows significantly. And then with Google, we also study some neural networks, especially relatively new neural networks that they use in their edge devices using edge TPUs. And we found out that more than 90% of the total system energy is spent on memory in these large machine learning models. So you can see that these devices that are quite powerful are spending most of their energy in memory. Okay, let me pull back a little bit. I'm going to argue that we need to design intelligent architectures going into the future. And these architectures are going to be making decisions for us. And we need to actually make the architecture itself intelligent so that it can actually make good decisions for us in a good way. So I would argue that the intelligent architecture needs to handle data well. So the rest of this talk is going to be about this, but a specific aspect of this. So how do you handle data well becomes a question then. I believe there are 3 directions in this. We should really ensure that we design our systems, algorithms, architectures, devices, such that data doesn't overwhelm the components. We're going to talk a lot about that. This is more memory-centric, data-centric design. I'm not going to talk about the second and third direction, not much in this talk. That could be a subject of separate talk. But also, we need to take advantage of the data and metadata that's flowing through the system. So today, when we design our systems, they're usually designed, we have controllers, we have decision-making structures that are heuristic-based. And these heuristics are determined by the designer, usually a hardware designer, sometimes the software designer also, sometimes hardware, software together. And these designers cannot really deal with lots of complexity. As a result, they have very simple policies to control a complicated system. For example, when someone designs a memory controller, the memory controller uses some heuristics to say, oh, if this row is open in this bank, I'm going to prioritize this request that goes to that row. That's a very simple policy, right? But there's a lot of information actually available to the memory controller that could potentially be used to make a better scheduling decision that takes into account longer-term performance impact of those scheduling decisions. So our systems today are actually very simple. They don't learn from their decisions. They don't take into account the vast amounts of data and metadata flowing through the system to make experience, to change their decisions based on experience. So humans are very different. For example, we interact with the system, we interact with our environment, and we make decisions based on what we see, right? We're very experience driven. So I believe we need to be much more data driven going into the future. We need to have much more machine learning based components that make decisions using machine learning algorithms in our systems. And I think that's a very interesting direction. We have actually a lot of works in this area. I'd be happy to talk about those separately. And also it is related to this data-centric component that I'm going to talk a lot about. And I think the third aspect of how to handle data well is actually understanding and exploiting properties of data. So if you think about data, data has lots of properties. It has security properties, privacy properties, compressibility properties, approximability properties, fault tolerance properties, locality properties. You can keep adding to these properties, basically. Today, if you look at how many properties actually get communicated to the hardware or the software, you see very little. The semantic properties don't actually get communicated. As a result, when you need to decide, when you need to make a decision to do something in the hardware architecture or software, you don't use this wealth of information, semantic information. What you do is, for example, again, I'll pick the example of a memory controller. What the memory controller does is it has two requests. It needs to pick one or the other one to schedule first. And then it says, oh, this bank is not busy, so I'm going to pick the request that goes to the bank that's not busy. But this may not be a good decision from a security perspective or privacy perspective, because by scheduling this request to that bank, you may actually be causing a side channel. But because you didn't know that this request was security critical. So if you actually have semantic information, you can make decisions that are much better. So this is the data aware aspect. So basically, I think I spent a lot of time on that slide because I think it's really important to have this vision, in my opinion. I think going forward, we need to make our systems much more data-centric as opposed to process-centric, make them much more data-driven, making decisions based on experience as opposed to designer-driven, and make them data characteristic aware or data aware as opposed to component aware. So today's systems actually do not take into account semantic information. And this is kind of our vision of a better architecture going into the future: data-centric, data-driven, and data aware. Now, in this talk, I'm going to focus on the first one, especially. So you can say that actually this is a huge task. This requires changes across the entire stack for most of the things that we do. And I agree. Certainly, there needs to be a significant change in terms of research and design environment to enable these in a sophisticated manner. But I will show you examples of these changes. And I also will show you some examples that are relatively small changes that can actually get us significant benefits. And if you're interested, we have position papers that talk about this topic, and you can find them online. Now, let's jump into the data-centric or memory-centric architectures, which is the first component. And I'm going to focus on the first component. Even if you look at this first component, if you ask the question, what should a data-centric or memory-centric architecture look like? I believe there are many properties over here. I listed 4 major ones over here. We're going to talk about the first one. We should really be processing data everywhere, in and near memory and sensor structures where it makes sense. But I think we also need to be designing our systems to be much more lower latency access and lower energy access to data. I think we need to look at emerging memory technologies, for example, or design of storage and memory systems and sensing systems such that we have lower latency and lower energy. This area needs a lot more attention going into the future. We have some work in this area, but I don't have time to talk about that. We need to, of course, enable lower cost data storage and processing because data is extremely large and important. And we also need to manage data intelligently because data is extremely important. I'm going to talk about this intelligent data management a little bit to motivate processing data where it makes sense. Now, let's jump into the main subject of this talk. It's essentially processing data where it makes sense. I say where it makes sense. Today, we have no choice. Today, you have to bring the data to a computing unit. It could be a CPU, GPU, FPGA, or machine learning accelerator or some other accelerator. And within that accelerator, you need to bring the data to the computation unit. So there's a very small place where you can do the computation. Where it makes sense means don't limit yourself. Enable computation capability everywhere in the system. It could be the storage, it could be the memory, it could be the sensor. Here are some examples over there. Enable computation capability everywhere, and then design the software and the entire software infrastructure, algorithm, all the way from algorithms to operating systems, etc., compilers, such that you can do computation in a distributed manner across the entire system, as opposed to limiting yourself to a processor. So that's the major idea, essentially. So this is not a new idea. This is an old idea. People have looked at this in 1960s. These are some early papers that we could find in processing in memory. They called it logic in memory at that time, near memory, as I will define some terminology in a little bit. And this is another paper that was written in 1970, but the research was done in 1960s. So you may say, okay, this is an old idea. People have proposed processing near memory a long time ago, and it never panned out. So why should we look at it again today? Why do we have hope that this will change? So I think there are two major reasons for this. First of all, we're having huge problems with memory technology, and there's a huge demand for actually data-centric computation from applications and systems. I'm going to examine both of them. I'm going to spend less time on the memory technology, but I'm going to give you some examples. And one of the issues today is our memory technologies are not scaling very well. So DRAM is not scaling very well. We have a lot of issues in terms of reliability, security, and safety. So these scaling issues can be solved by having intelligent controllers near memory that can do some computation, essentially. That's the idea. So if you actually start adding controllers that can do computation to solve scaling issues in memory, you can actually do computation for applications in memory as well. So that's one part. And the other part is we have a huge data access bottleneck. Energy and power are big bottlenecks, and data movement energy dominates computation energy in today's systems. And today we're greedy. We need both performance, energy, and sustainability all at the same time. So we don't want a trade-off between performance and energy. In the past, we used to say, okay, to get 5% performance, I can expend maybe 3% energy. We don't want that, basically. We want 5% performance and 5% energy reduction at the same time. So we can improve all metrics by minimizing data movement. So today's systems are kind of squeezed in the middle. At the lower end, technology and devices are pushing us to have more intelligence so that scaling becomes better. At the higher end, applications, our systems are actually pushing us to actually do something around memory so that we can scale better and get rid of some of these bottlenecks. Now, let me give you the lay of the land a little bit. Today, actually, processing in memory is happening. They're prototypes. They're 3D stacked machines that look like this. You have logic layer under memory layers, and you can do computation in the logic layer. I'm going to talk about that if you have time. And then there are experimental chips like automata processor from Micron, which did not succeed that much. But more recently, the RowHammer company in France designed DRAM chips that can actually have computation units inside it next to each bank. I'm going to hopefully talk about that if you have time. And even more recently, Samsung, SK Hynix, these companies have designed DRAM chips where you can actually do accelerate machine learning applications. They have matrix vector multiplication units inside them. So these are more specialized chips. RowHammer is more general purpose, but these exist today. RowHammer you can actually buy today. We have a lot of experiments with RowHammer chips, for example. Also, Samsung and Meta, Facebook, have designed these memory modules where you have a buffer chip. Inside the buffer chip, you can do computation for recommendation inference. And Alibaba itself, which is an infrastructure company, clearly, they have designed their own DRAM chip to do computation for recommendation inference as well. And there are many other experimental chips and startups. These are actually very interesting prototypes. Some of them you can buy, some of them you can get access to. So today, it's a vibrant area that shows that people are actually doing processing near memory. Okay, let me talk about the technology perspective, and then I'm going to motivate it from the application perspective a little bit. So basically, memory technology scaling is a tough problem, and we've been working on this problem for a long time now. This is one of the papers, position papers that we've been writing. I'm going to give you a couple of examples to show that the issue is actually pretty tough to solve without having intelligent controllers in memory. So, for example, one of the studies that we did in 2012 to 2014 was on RowHammer. In RowHammer studies, we showed that you can actually predictably induce errors in most DRAM memory chips by keeping on activating a single row many, many times. This is a technology scaling problem because cells are too close to each other. And because the cells are too close to each other, you have interference between the cells. And this interference affects the data that's stored in the cell. Clearly, this should not be happening, but it's happening in existing systems. Okay, let me quickly give you the issue. In memory, you have a bunch of rows. And if you actually activate one row, you need to apply high voltage to that row that enables you to read the data from that row. Now, if you want to activate some other row, you apply low voltage to this row, which is called a pre-charge in DRAM, and then you can activate some other row. Now, if you keep doing this repeatedly, activate pre-charge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, it turns out some cells that are physically adjacent in physically adjacent rows get corrupt. So they go from 1 to 0 or 0 to 1. Because you have caused electromagnetic interference to those cells by doing this toggling of the word line from high to low voltage. Now, clearly, this should not happen because this really breaks memory isolation. And as a result, this could be a security problem. This could be a safety problem. It could be just data corruption problem that causes you to lose data. I'm not going to talk about this in a lot of detail, but I'm showing this to you to motivate that this sort of issues exist. They're becoming much worse in the field. And in our original paper, we showed that more than 80% of the chips that we've tested from 3 major DRAM manufacturers are actually vulnerable to this problem. And there are only 3 major DRAM manufacturers in the world today. They occupy more than 97% of the DRAM market. And people have shown that these bit flips are not only a data corruption problem, but also someone can take advantage of these bit flips to take over your system, because someone can actually cause these bit flips in the page table structures, and a user level process can get access to its own page table, write access to its own page table. As a result, all bets are off after that. I like this quote over here. It says, "Forget software, now hackers are exploiting physics." This is someone else, of course, writing about to talk about that in a separate time. And if you're interested in lectures in RowHammer, there are a bunch of lectures. Now, okay, how do you solve this problem? This is just one example problem. To be able to solve this problem, we've always argued that you need intelligence in the memory controller. Memory controller needs to be able to figure out something and fix this problem, basically. And our argument, actually, we actually designed a lot of intelligent controllers. I'm not going to talk about them, but I'm going to talk about what industry did finally. This is in ISSCC, which is the major circuits conference. In February, SK Hynix, these are folks from the second major DRAM manufacturer in the world, they wrote this paper. It's a nice paper. Finally, they acknowledged the RowHammer problem, and they said basically they solved the problem or mitigated the problem by having more intelligent memory controllers that can track these aggressor rows, for example, and also that keep counters in DRAM per row, such that they could refresh the rows that are refresh the adjacent rows of the rows that are activated a lot. I don't want to go into a lot of detail, but in the end, they changed the DRAM chip such that they have an intelligent controller inside, as we have envisioned. So in the and now a lot of the solutions are actually similar to the solutions that we've been discussing in literature. So this is actually a very good example of why we have been motivating processing in memory using these intelligent controllers. It's an intelligent controller that people have inside DRAM today. And if you're interested, Samsung also has a paper that talks about something similar, except it's on archive. Okay, so the question is, of course, are these issues going to continue, or are these issues going to become better so that we won't need intelligent controllers in the memory chips? I would argue that as memory technology, memory cells become smaller and smaller, which you need to store lots of data, you will have these issues more and more. And more recently, we've shown that these issues actually become worse. There are other read disturbance mechanisms in DRAM, and this is the row press mechanism. I'm not going to go into the detail, but if people are interested, you can read this ISCA paper that we wrote just this year, in June, less than 2 months ago. Okay, you can say that DRAM is a technology that's dying. I don't agree with that necessarily, but it's an old technology, clearly. You can say that this technology will be replaced by some other technology that's not going to have these problems. It'd be good to examine those technologies, but unfortunately, we actually have been doing a lot of work on emerging memory technologies as well. Unfortunately, emerging memory technologies all have their problems. For example, phase change memory has an endurance problem. And in order to actually tackle the endurance problem, you need an intelligent memory controller. It also has some other problems like write disturbance, etc. You need an intelligent memory controller. So these intelligent memory controllers are needed to actually make sure that the memories work correctly. And flash memory is another example where you definitely need intelligent memory controllers today. Okay, so I think I spent a lot of time on this technology scaling, but I think it's good to motivate why we need intelligent memory controllers in a different perspective than just, oh, applications need it. Actually, memory is also needed, and these intelligent memory controllers can avoid many failures and enable better scaling. Now, let me switch gears to the application side and system side. I've already mentioned this, so I'm going to go through this also relatively quickly. But on the systems and application side, we have a lot of problems as well. Data access is a major bottleneck, energy consumption is a key limiter, and data movement energy dominates computation energy. In my opinion, actually, we have a choice to make. Do we want a world that looks like this in the near future, or do we want a world that looks like this? I will pick that first one, but I don't want to actually give up the productivity of the second one. So as humans, we're greedy. we should be shooting for both high performance, energy efficiency, and sustainability all at the same time, I would say. Now, unfortunately, our design principles goes against all of these at the same time. Why? Data access is a major performance energy bottleneck, and the way we design our systems, computers, immediately break all of those goals that we want to achieve. Remember, high performance, energy efficient, sustainable. Why? We're moving data across the system. And by moving data, we're causing a lot of energy waste. By moving data, we're actually causing a lot of performance loss as well. Now, in order to overcome the performance loss, we complicate our systems. We actually do a lot of levels of multi-threading, heavy levels of out-of-order execution, many levels of cache hierarchies, prefetchers, etc. These complicate the system. Now, when they work, they actually reduce the performance loss. They improve performance. Really, they don't work, or they waste time. As a result, they actually compound the energy waste. We're moving data to which increases energy fundamentally, and to overcome that data movement, we're adding a lot of complexity to our systems. Unfortunately, that complexity is not working. As a result, it's causing extra energy. So we're in this vicious cycle today. And the main reason is we have limited ourselves to processing data to only one place, which is the computing unit. Okay, so as a result, we're very processor-centric. All data is processed in the processor at great system cost. And we know that this is bad for performance. I'm going to give you some anecdotes very quickly. This is a one-page paper that was written by Dick Seitz, who was a chief architect of Alpha in 1990s. He basically wrote this paper. It's very stupid in one page. And he basically said that we designed this top-of-the-line processor. It's the best in the world at the time. It can finish 4 instructions every clock cycle. Unfortunately, on this important workload, database workload that we think we designed it for, it's finishing 1 instruction every 4.7 cycles. Basically, it's operating at 5%, about 5% of its peak efficiency. Why? It's waiting for data to come back from memory. And he basically ends this article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, this is my own PhD thesis. Together with Intel, we actually collected a lot of data, and we showed that most of the time, a top-of-the-line Intel processor is waiting for data to come back from memory. Okay, and this is Google's work. If people are interested, this was published in ISCA 2015, 10 years later. And it basically shows essentially the same thing. According to Google, these are their data center workloads, and most of the time, the processor is waiting for data to come back from memory. A very, very small fraction of the time, it's actually finishing instructions, 10 to 20%. So these are top-of-the-line processors, and most of the time, they're idle. Okay, that's computation. As a result, we're wasting a lot of performance. Now, if you look at energy, the story is even worse. If you look at energy, basically, this is the energy. These are results from Bill Dalley's high peak presentation. You could argue with all of these numbers, but the trend is the same. This is a 64-bit double precision floating point operation. It's 20 picojoules. This is a DRAM access, 16 nanojoules. So if you look at that disparity, it's 800x. Then the question is, does it really make sense to do 2 DRAM accesses to bring 2 pieces of data to the processor to do a very energy simple operation and then write back the data with 1 more DRAM access? In order to overcome that energy differential, you need to actually have a lot of locality in your caches. And that's a lot of locality that is very hard to get in today's workloads. So basically, a memory access today consumes 2 to 3 orders of magnitude the energy of a complex addition. If you want to look at a simple addition, a 32-bit simple integer add, the disparity is even higher. A memory access consumes 6400x times the energy of a simple integer addition. Okay, so as a result, we see this huge energy waste in the workloads. More than 60% of the total system energy is spent on data movement, or more than 90% of the total system energy is spent on large machine learning models. And this is going to get worse. So I would argue that we do not want to move data. We actually go to a system design paradigm where we can enable computation with minimal data movement. We should really compute where it makes sense, where data resides. And we want to make computing architectures more data-centric. So this brings us to now more ideas that are based on this. We're going to talk a lot about processing inside memory and storage, but these ideas can be applicable to the sensors, interconnect, everywhere where you have actually data in the end. I'm going to talk about memory and storage because these are interesting. Memory is especially interesting, but storage is increasingly interesting. So we want to store applications. We want to ask memory, memory, can you execute this function or this application for me? And the memory returns the results. So fundamentally, this is still an accelerator model. In the long run, we want to have a distributed system where everything is equal and everything is programmed as a processor. And that processor may be in the memory side or the storage side, and they could be a specialized processor, of course. So there are many questions, even in this accelerator model. How do we design the compute-capable memory and the controllers? How do you design the processors and communication units? How do you design the software and hardware interfaces to enable this sort of operation? How do you design the system software, operating system, virtual machines, compilers, and languages to take advantage of this and make it easier? How do you design the algorithms to take advantage of the memory and storage computational structures? I'm going to talk about that a little bit when we talk about processing using memory. And also, I think from a computer science perspective, how do we rethink the theoretical foundations of computing? If you think about theoretical foundations of computing, today, when you look at algorithmic complexity, we count operations. And operations are cheap, as I showed you, right? It's really about data movement. So we need to have a much more data-centric theory of computation going into the future. So this is a problem that spans across the stack, as you can see from this question. And we're going to look at that stack in a little bit. I'm going to talk about some ideas, but we don't have time to cover all of the ideas. So we have this paper that we keep updating on arXiv. If people are interested, they can take a look at it, and they can learn a lot more from it than I can cover in this lecture. We also have a processing in memory course that people can attend, as I mentioned, and we keep giving it at different times. And a solid-state drive course and a genomics course, as I mentioned. I will also mention that we have some real processing in memory tutorials. There's a lot more information out there than I can cover in this lecture. And in these tutorials in ISCA, ASPOS, HPCA, and there's one upcoming at Micro, we talk a lot about different processing in memory approaches and systems. And we have invited talks from Samsung, SK Hynix, Alibaba, and also IBM, for example. And we're organizing one at Micro in October. So if people are interested, these are all open. Everyone can attend on YouTube, and everyone, all of the slides are available. Now, let me jump into some ideas. Are there any questions on the previous talk, part of the talk? I know this is more motivation, but if people have questions, I'm happy to take them. Okay, if nothing at this point, then I will talk about two approaches to processing in memory. So processing in memory is interesting because there's a lot of terminology issues over here. I'm going to focus on memory from now on, a little bit storage. And I think there are two fundamental approaches to processing in memory. They're fundamentally different. Processing near memory is actually easier to adopt. That's why we're seeing a lot of processing near memory prototypes. Now, let me give you the definition. Today, you have the processor here and the memory here. They're far away from each other. Now, if you actually put the processor or logic closer and closer and closer and closer and closer into the memory, you get nearer and nearer memory, but logic and memory are still separate structures. You design them separately, and you get them closer to each other in some way. So this is very similar to the way we are designing our systems today. Processor and memory and logic are separate, and logic is the way we design it today. It could be a CPU, GPU, FPGA, accelerator, or some random logic block that can do computation, right? So in this sense, this is easier to adopt, and this is why it's happening in real systems today. Now, processing using memory is fundamentally different, and I'm going to focus on that one first. And then if you have time, we're going to talk about near memory. So you have processor here today, and then you have memory here. Forget about the processor. Look at memory only. And this memory, normally, we don't think of memory as doing computation. But any type of memory has some analog computation capability. And we're going to use that capability to do processing. That's the idea of processing using memory. You use the computation capability, inherent computation capability of memory for performance improvement or energy reduction. So actually, PIM processing in memory is an area where terminology is unfortunately not very well done. I tried to actually give a taxonomy over here. I think there's a nature of computation. Do you use the memory or do you add logic near memory? There's a technology where you actually can do the computation. And there are many technologies of memory technologies today. Some of them can be combined, like 3D SRAM, for example, or 3D DRAM. And then there's the location from the perspective of the system. Is it in the sensors? Is it in the cold storage, hard disk, SSD, etc.? And in the end, a three-tuple of these determines the PIM type. You may have processing using DRAM in main memory, for example, which I'm going to talk about. And one can combine multiple processing in memory types in a system also. So I think using this taxonomy, we can navigate the processing in memory landscape in a much better way. But before jumping into processing using DRAM, I will also say that we're going to still treat memory as an accelerator at this point. But going forward, this may change. Now, let me give you an example PIM type. I'm going to talk about processing using DRAM, which is an area which we've been doing a lot of research in. Here, the nature of computation will be using memory, using the analog computation capability. Technology will be DRAM, which is the major main memory technology, and the location is main memory. So we're going to talk about some examples of processing using DRAM in main memory. Now, to give you a summary, we can support a lot of operations basically using inherent computation capability of memory. You can support bulk bitwise AND, or NOT, and majority operations. We can support bulk bitwise copy and initialization operations. We can do true random number generation, physical unclonable functions in memory, like security functions. And we can also do more complex computation using lookup tables at low cost. And the fundamental idea is to exploit the analog computation capability that exists in DRAM. And one of the ideas, sub-ideas, is to activate multiple rows. I'm going to give you some examples of this. And we see significant performance energy improvements using this. Now, let's start simple. Let me give you some real ideas right now. So normally, we don't think of data copy and initialization as computation, but this is where some systems spend a lot of their time. So there are many applications of data copy initialization in our systems. In operating systems, we initialize pages to 0, for example. We do forking. We do cloning of virtual machines, page migration, etc. And Google, in their ISCA 2015 paper that I mentioned, actually showed that only these two function calls that move and copy data occupy 5% of the execution cycles in all of their data center workloads. This is fascinating, I think. Only two function calls occupying 5% of system cycles. Now, how do we do copying today? Basically, we have to go through the processor. If you want to copy this white page to this gray page, you have to go through the processor to do it byte by byte. You're basically exercising an unnecessary part of the system. The idea of in-memory copy is not to go through the processor and do it inside the memory. And basically, the idea is this. You copy the white page to the gray page. And this is low latency because we don't move the data through the memory bus. This is low bandwidth utilization on a very important system resource. We don't waste the bandwidth of the memory bus. This is no cache pollution. You don't go through the cache hierarchy, and no unwanted data movement. Essentially, you move the data to the computation unit or out of the memory only when you really need to do so. And I'm going to show you a mechanism that takes a 4 kilobyte page copy from about 1,000 nanoseconds to 90 nanoseconds, and 3.6 microjoules to 0.04 microjoules. And this is unoptimized. So the idea is called row clone. And the idea is very simple. You basically have a bunch of rows in DRAM that are connected to a row buffer, sense amplifiers. And essentially, we're going to do two consecutive activates. We first will activate the source row. And once you activate the source row, the data gets copied into the row buffer using the sense amplification and chart sharing process. Now the data is very strong inside the sense amplifiers in the row buffer. The next step is to activate the destination row, which implicitly deactivates the source row and then connects the sense amplifiers to the destination row, row B. Basically, by using the row buffer as a temporary buffer, we copy data from row A to row B with minimal amount of data movement in DRAM. This is the best we think we can do in DRAM without modifying the structure. In fact, in this case, the hardware cost is negligible. In fact, as I will show you soon, you can violate the timing parameters of DRAM to mimic this operation in off-the-shelf DRAM chips that are not specified to do this operation. And you can do this operation very reliably. So you can do this in existing DRAM, basically. So we have shown in our work that you can reduce the latency of a 4 kilobyte page cut by more than 10x and reduce the energy by more than 70x. So these are very large numbers. And clearly, this can actually simplify the design of the software as well, which I'm not going to talk about here. Ignore these other bars over here. We have actually improved this significantly. And the latency and energy actually of copying data between different banks and different subarrays in DRAM has reduced significantly. Okay, and that's the paper. And there are application level results in the paper. And more recently, 6 years after the publication of our paper in Micro 2019, these folks from Princeton showed that by violating the timing parameters of real DRAM chips using a soft-MC infrastructure that we have actually open sourced in the past, you can do row clone. You can actually mimic row clone reliably in most DRAM chips. This is actually fascinating. And we've replicated their results in our PyDRAM work. This is a work that we published recently at TACO, where we showed that you could actually do row clone and true random number generation using off-the-shelf DRAM chips. These are DRAM chips that are not specified to do these operations. We just violate the timing parameters such that we can do back-to-back activations. And that way we can actually do reliable data copy. And we can actually look at the system level effects of them. You can actually run an application and do the copy inside the DRAM and look at the benefits of that copy at the application level. Or random number generation. I'm going to talk about random number generation a little bit. If people are interested, you can do a lot of interesting studies if you can use. Okay, I will skip this because we don't have time. So there are a lot of lectures on this topic also. Now, I've talked about copy, initialization, and a little bit random number generation. What about true computation? What can we do in DM? So basically, we've shown that you can support in DM a majority function and or function and not function. And I'm going to show you that example. But before I show you the example, I will say that new memory technologies enable even more opportunities. So there are a bunch of new memory technologies. They have a very, very small fraction of the market today, unfortunately, but maybe going into the future, they will grow. These technologies are fundamentally more efficient in the sense that reads are not destructive. In DM, when you read data, because of chart sharing, you destroy the data in the row. As a result, fundamentally, you need to move the data somewhere else to be able to operate on it. Whereas here, you don't need to do that. And also, because of their structure, they can enable matrix vector multiplication. But take that with a grain of salt because these technologies are not mature yet. I think going forward, we need to examine how these technologies will evolve. Okay, let me give you what we can do in DM. In DM, you have rows. I'm showing you an example of 3 rows over here, A, B, C. I'm showing you 1 bit in each row, but imagine that the row is actually 8 kilobytes or so. So you can actually do this operation on 8 kilobytes of data, 3 input data, and then you can do this in 1,000 subarrays. So you can do this in 8 million bits or 10 million bits, depending on how big your subarrays are, how many subarrays you have. And the idea is very simple here. The idea is triple row activation, as I said over here. You activate concurrently these 3 rows. Now, if you actually concurrently activate these 3 rows, based on circuit level principles, all of these cells get connected to the bit line, and the bit line gets perturbed based on the majority function, bitwise majority function. What does that mean? If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. In this animation, at least 2 of these cells are charged. So in the end, the bit line contains the charge state. And the final state is actually bitwise majority, which is a great function. Now we've actually computed a bitwise majority without adding any logic to DM. We're exploiting the chart sharing principles and triple row activation. Well, we did add logic to activate 3 rows, of course. So you need to have some logic, but that's not logic to do computation. That's logic to do triple row activation. So majority function is interesting. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So now you can have bitwise OR, bitwise AND. That's very good for database operation, as we show in this paper over here. Now, you don't have functional completeness because we're missing a NOT, but NOT is actually there. If you look over here, if you activate 1 row, you read the data over here, and complement of the data is on the other side of the sense amplifier because of this sensing structure. Now, if you can actually put that back into the subarray or somewhere else, you can actually get the complemented version. So that's how we get the complemented version. I'm not going to talk about it. This requires a little bit more logic, but the logic is, again, not to do the NOT operation, but to actually move the data to the appropriate place. Okay, so now we can actually have a functionally complete AND or NOT and majority function bitwise, block bitwise. It's a very special type of operation, but it's very different from what we can do using a processor, right? Using a processor, you can do any operation. Here we have bulk bitwise operations, but you can actually write any algorithm to take advantage of this. You just need to think about your algorithm in a very different way. Now, fortunately, there are a bunch of algorithms that are written to do a lot of bulk bitwise computation, like databases and web search, and also there are some others. And in our paper, we looked at database queries, for example, and we showed that if you actually port and implement these database queries on this bulk bitwise execution engine in DRAM, you get significant performance improvements and energy improvements. Again, I don't have time to talk about it, but that's the idea over here. So we call this in DRAM bulk bitwise execution engine, and this is the paper that actually introduced the full functionally complete execution engine Ambit. I think there's a lot more work to be done in this area, and we cover some of that work in this bulk bitwise execution engine paper. I look forward to seeing a lot of work, and we'd be happy to help in any way. So the question is, of course, how do you make this more programmable? And more recently, we've been targeting how to make it more programmable. This is a paper that was published in ASPLOS 2021. I'll give you the basic idea. Essentially, we wanted to make it such that programmer can specify any type of logic using these operations. And then we generate a majority inverter graph, which is actually used in quantum computing today. And then we can optimize it using some design automation tools. And then the next step is to implement that majority inverter graph using commands in DRAM. So there's some translation that needs to happen into a microprogram plus some allocation, etc. And essentially, the desired operation, which could be a convolution, for example, or it could be a matrix vector multiplication. It could be just any type of division or multiplication that can be implemented using a micro program, essentially DRAM command, sequence of DRAM commands. And this can be stored in main memory. And when the program calls that operation, matrix vector multiplication, this gets shipped to the memory controller, and the memory controller essentially executes the micro program to execute that operation. This is a programming model that actually takes advantage of these block bitwise operations, but it's compatible with the sequential programming model that we have in today's systems, because an instruction triggers this block bitwise operation, and that instruction can be implemented using DRAM commands, essentially. Okay, so I don't have a lot of time to go over this, but we show that you can get significant performance energy improvements over both CPUs and GPUs using complex DRAM operations in this particular case. And there's more on this, and we have some more work coming up. There's actually work that Yahoo has done on this topic. They've been looking at compiler support for bit serial SIMD processing. And I think there's actually a lot of exciting work that could be done in this area going forward. Now, I'll quickly mention that processing using memory is nice, but it's a bit limited. How do you do complex operations? In this work, we tackled that question. To be able to do really complex operations like multiplication or some sort of averaging, etc., we have used lookup tables, and I will refer you to the paper. Lookup tables enable a lot of interesting computation, essentially. And this is a paper that was published in last year's Micro. I will quickly mention that you can do other things in DRAM by, again, exploiting the analog operational properties. If you access DRAM, and if you reduce the latency to a level that's not allowed, some cells fail all the time. And it turns out these cells are unique to the DRAM device. Essentially, they are physical unclonable functions. So by reducing the latency to a level and identifying which cells are actually physical unclonable function cells, you can use the DRAM device as an identifier. And this could be useful for remote attestation, for example. So in-memory techniques can benefit from this. We also show that, and these are actually shown using real devices. Using real devices, you can reduce the latency, and then some cells fail, and they fail randomly. 50% of the time they fail, 50% of the time they don't fail. So this could be a random number generator cell. So you can actually generate random numbers quite efficiently inside the DRAM this way. So these papers actually talk about that. And we've actually found out even more efficient methods, high performance methods of generating random numbers. So I find these fascinating because once you start doing computation on the memory side, you want to put some security critical functions on the memory side as well. And you need this sort of infrastructure to do remote attestation and random number generation. And I believe there's more to do in this area, like encryption, randomization, etc. And there needs to be more work in this area for sure. Okay, so maybe I will also mention that we actually do a lot of work in flash as well. So flash memory is also the dominant memory technology for storage today, or SSDs. And in flash memory, you can actually do similar operations. I'll give you the basic idea. Essentially, we can do multi-operand bulk bitwise operations using single sensing and at high reliability, and we see significant performance and energy improvements. And you can do this with no changes to the flash cell arrays. Let me give you the idea. Essentially, you look at a flash chip. When you actually activate 32 rows concurrently, you can simultaneously sense them if they're in the same block, and you get a bitwise AND of 32 rows. So you have 32 input AND gate across 16 kilobyte of data, very large amounts of data, essentially. And in this paper, we basically show that this is reliable. You can make it reliable in real flash chips. And the reason it works is essentially because of the way flash memory operates. If you simultaneously activate multiple word lines in the same block, a bit line reads as 1 only when all of the target cells store 1. If one of the target cells stores 0, then you get an open bit line over here, open circuit. As a result, you get a 0. So this is a bitwise AND function. Essentially, this is fascinating, and in our paper, we show that you can do 48 input bitwise AND in real flash chips. Now, you can also have a bitwise OR function. If you actually do this activating multiple rows operation, multiple word lines in different blocks, different flash blocks, you get the bitwise OR because of the way different blocks are connected to each other. Now, if you have a very reliable bitwise OR, it's not as large because latent bitwise OR. Okay, something went a bit slow. Okay, but basically, this is a complete execution engine. Sorry. We can also enable other types of bitwise operations. Flash memory already has an inverse read function, so we actually have NOT, and we can have NAND, NOR, XOR, XNOR. And this is actually fascinating, I think. If you're interested, you can read this paper. And the upside is there are no changes to the cell array, and you can have many operands with a small increase in sensitivity computation results such that you don't observe any bit error in the tested flash cells in our work. Now, the results are actually very promising. We see significant performance and energy improvements compared to prior works in operations. You get actually larger improvements. Okay, so we're almost at the end of the processing using DRAM. If you have time, I'm going to talk about processing near memory, but if you don't have time, I'm going to conclude. But I will mention emerging memory technologies. So we talked about DRAM, we talked about flash. These are fascinating, and I think we should be improving them. But emerging memory technologies are also quite interesting, and there are quite a few works in this area. This is one work that builds on our row clone and ambit works that basically shows that you can do bulk bitwise operations in emerging non-volatile memories like phase change memory, and they actually show good results as well. And emerging memory technologies can also do other things like matrix vector multiplication. Because of the three-dimensional crossbar array structure, you can actually do analog computation using Kirchhoff's laws, and you can feed in a vector, and the matrix elements are stored in the two-dimensional structure over here. And as a result, as you feed in the vector, you do analog multiplication of that vector using the matrix element that are stored in the array. And there are many works that talk about this. You can see some of the earlier papers on this topic that talk about how to do matrix vector multiplication in emerging memory technology using analog computation. I don't have time to talk about this, but I think this is also important. And I believe there are a lot of issues that need to be solved in these emerging technologies because they're not there yet, but research needs to be done in all of the technologies. And maybe I believe we need to combine these different technologies in the end, just like different technologies are combined today in our systems. Okay, I talked a lot. I think right now we have a choice to make. I've done with the processing using memory part. I can talk about processing near memory, or we can conclude